Hi everyone! In the last video, we encountered solids with bounds that are more easily described using the variables r, theta, and z. This happens when our base region is like a circle. Then it's better to use the polar coordinates on the xy plane to describe it. Okay, so the variables r, theta, z. These variables are called 3D cylindrical coordinates in space. Okay, so if just r and theta, we call them polar coordinates. And they are in the xy plane, right? But now we have three variables, r, theta, z. Then we call them 3D cylindrical coordinates in space. So let's talk about triple integrals in cylindrical coordinates. The cylindrical coordinate system consists of the variables r, theta, and z. These have the usual meaning. So in the three-dimensional space, r measures the distance to the z-axis. So it's not distance to the origin. It's only to the z-axis. The relationship between the Cartesian coordinates are just as before. Okay. So if we have on my other handout, I have this picture. Okay, so here, this bottom. So for any points P, you can, let's see here. So for any point P, R is the distance from the points to the z-axis. Okay, so this is the R. If we project this point down, we get the point Q, right? If we project down to the xy plane, we get the point Q. And then R is the distance from Q to the origin. Okay, so this is R. So on the xy plane, we can still have the polar coordinates, right? We have the relations x. So x equals r cosine theta, and y equals r sine theta. So far so good. And z is z. Okay, so and then here you can see we're gonna learn three coordinates. We have the Cartesian coordinates, also called rectangular coordinates, x, y, z. We have the cylindrical coordinates, and after we talk about cylindrical coordinates and do some examples, we will talk about spherical coordinates. Okay, so cylindrical coordinates, we have r, theta, and z. So how do we change from rectangular coordinate to cylindrical coordinates? Okay, so given r, theta, z, how do we express x? Well, x is r cosine theta, y is r sine theta, z is z, right? So this is, we were having some cylindrical coordinate and we want to convert it to rectangular coordinates. The other direction, when we have the rectangular coordinates and we want to get the cylindrical coordinates, well, r is the square root of x squared plus y squared, and we know tangent theta equals y over x, right? Tangent theta is, look at this triangle. Tangent theta is opposite over adjacent. So that's why sine theta over cosine theta is tangent theta. Then we have y over x. Okay. So in order to solve theta, because the arctangent only covers, so you know the tangent like this, well, the arctangent is, we use this piece and then make the mirror image across the line y equals x. So this is arctangent of x, let's say. Okay, so the arctangent, the range is only from minus pi over 2 to pi over 2, not included the endpoint. So, which means it's only covered the first quadrant and the fourth quadrants. So if the point is in the first quadrant or the fourth quadrant when we project to the xy plane, then theta is arctangent of y over x. If the point is on the second or third quadrant, when we project to the xy plane, then the theta is pi plus arctangent of y over z. Y over x. And z is still z. So this is how we interchange between rectangular coordinates and cylindrical coordinates. Let's continue. So yeah, when we were putting surface integral, we saw that a small increments dz in z and a small increment d theta in theta give rise to area differential. So look at this guy. This guy is dz, and then this guy is r d theta, right? And dr measure the width of this this patch, okay? Yes. So this surface patch, we have r times dz d theta, okay? And when we compute triple integrals, a small increments dr in r adds a thickness to this patch. The volume of the solid is approximated by the area of the patch times the thickness, dr. So volume differential in cylindrical coordinates equals r dz dr d theta. Okay, the order may interchange, but don't forget we always have an r in front of it. Okay, so think about that. You know, dv is like dz times the area differential on the xy plane, and the area differential is r dr d theta for polar coordinates, right? So it is consistent with what we learned before. Next, let's look at this example. Consider the solid E that lies in the first octet and is bounded by the cylinders x squared plus y squared equals 25 and the plane y plus z equals 5. Set up but don't evaluate a triple integral that computes the volume of E in cylindrical coordinates. So let's draw some picture. Okay, so here we have a cylinder, okay, and with radius 5. Okay, and how about y plus z equals 5? Well, this is a line, but it has no x in it, right? So we know it's gonna be parallel to the x-axis. So it cross the y-axis and z-axis. When does it cross the y-axis? Well, that is when x and z is 0. Then we have y equals 5. Okay. And then what's next? And it also pass the z-axis. Let's plug in when y and x is 0, we get z equals 5. So it passed through those 2 points. Then we can connect them together. And this is a plane, right? And how would that cross this cylinder? So imagine we get something like this. Can you imagine, everybody? And in the first octet, then which is right here. Okay, so let me change a different color. So this is the region. Can you imagine, everybody? Okay, so we want to compute the volume, okay, in cylindrical coordinates. Now let's see. So the volume equals, so we want to compute volume, so that's 1. And then we have dz dr d theta. Okay, so we look from the outside. Theta, well, theta, when we project this solid down on the xy plane, we get this region. Okay, so this region, the theta goes from 0 to pi over 2. Right? And then how about the r? Well, the R is from 0 to 5. And then how about the Z? So any points on this region, when we go to the Z direction, you can see the lowest point is when Z equals to 0, and the upper point is when Z is on the plane. On the plane, so Z is a function of on the plane we have y plus Z equals 5. So Z equals 5 minus y, but because we are using cylindrical coordinates, we want to have Z as a function of r and theta. So we want to express Z in terms of r and theta. Okay, and we know that y equals r cosine theta. Okay, so we have Z is from 0 to 5 minus r sine theta. Oop. Oh, that kind of shifts. Okay, so far so good, everybody. So this is how we set it up. Oh, don't forget, we have an r here. So we can also try to integrate this integral. Let's do that. So first, integral of 1r, so integral of r with respect to z is r times z, right? Evaluate from 0 to 5 minus r sine theta, dr d theta. So that equals, here we plug in z equals 5 minus r sine theta. When we plug in z is 0, we just have 0. Okay, and what is this guy? Well, we can distribute. Remember, we don't have product rule, but in this case, we can distribute 5r minus r squared sine theta dr d theta. And now we're ready to integrate. So when we integrate 5r, we get what? We get 5r squared over 2, and then r squared become r to 3 over 3. We still have the sine theta. Okay. Sorry about, there's something wrong with my word. It keeps shifting what I write, and I already closed it and opened it, but it still doesn't work. Okay, so let's see. We evaluate from 0 to 5, so we have 5 squared is 25. 25 times 5, 125 over 2, minus 5 cubed is also 125 over 3 sine theta. When we plug in r0, we just get 0. So integral of this guy with respect to theta, first guy we just have 125 over 2 times theta, while integral of sine is minus cosine. Evaluate from 0 to pi over 2. So when we plug in pi over 2, we get this guy. And subtract when we put in 0, it's gone. The second term, we plug in cosine. Cosine pi over 2, you know, cosine looks like this. So cosine pi over 2 is 0. And then when we plug in cosine 0, is 1. So our answer is 125 pi over 4 minus 125 over 3. So far, so good, everybody. So this is the volume of the solid. Okay, let's continue. So next example. Evaluate the integral by converting to cylindrical coordinates. Okay, so here we are given the triple integrals in rectangular coordinates. So based on this triple integral, we gotta draw the region first. And after we draw the region, we can then convert it to the cylindrical coordinates. Okay, now let's see. We draw x, y, z axis. Okay, we look from the outside to the inside. The outside is the x, so we have a little width here, dx. Dx is from 0 to square root of 2. Okay, and then next we have the y. So we draw the rectangle there. So y is from, it could be negative. So y is from, this point is negative square root of 8 minus x squared. This guy is positive 8 minus x squared. Do you know what that is? So if y equals that, it means y squared equals 8 minus x squared. It means x squared plus y squared equals 8. And then this is a circle with radius. This is a circle with radius square root of 2 over 2. Okay. So far, so good, everybody. My circle doesn't look very good. Anyway. Okay. So that is the circle. And then on any point on this circle, we can go parallel to in the z direction. Then we have -1 to 2. So -1 is down there. -1 to 2. 2 is here. So you can imagine this is a cylinder. So far, so good, everybody. Okay, now let's see here. This is this whole cylinder, and z goes from -1 to here, 2. Okay, so if we use the and actually this is only the half cylinder because my x is from 0. So from 0 to, so this is half circle, and then so we have the half cylinder. Is that okay, everybody? Okay, so we have this half cylinder. Okay, so when we set it up, so we have, okay, we know our volume differential is r dz dr d theta. And then 1 plus, you see x squared plus y squared, we need to convert to the cylindrical coordinates. X squared plus y squared is r squared. And then z also goes from -1 to 2. Okay, now how about theta? Well, when we project on the xy plane, it's just like this guy. So theta is from -pi/2 to pi/2. Okay, on the xy plane. And how about the r? Well, r is from 0 to the radius. The radius 2 square root of 2. So this is the triple integrals in cylindrical coordinates. You can see now, wow, we're able to integrate because of this r, we can use u substitution. But previously, it's more complicated because the bounds it's like a functions, but now all 3 bounds, they're constants. So this integral is easier. So usually if you see, so we mark, if you see the base region, okay, base region, I mean when you project the solid onto the xy plane, you get the base region. So if base region is a disk, so then think about cylindrical coordinates. Okay, and in general, z is a function of r and theta. Okay, let's continue. So we integrate with respect to z. Okay. And in this order, we assume that r is a function of theta and z is a function in terms of r and theta. But there could be other cases. Maybe you have the r is a function of z and theta. Then you can just switch the order. Okay. So let's integrate with respect to z. Then it's the same thing. And we have the z goes from -1 to 2 dr d theta. And well, that's the same as we use 2 minus 1, which is 3. We can pull the 3 out. And then we have integral 2 square root 2 1 plus r squared r dr d theta. We can then use u substitution. Okay, let u be the expressions inside the square. Then du equals to r dr. Then r dr equals 1/2 du. So far so good, everybody? Okay, now let's see. 3 stay here, minus pi over 2 to pi over 2. And okay, this guy is integral of u of 0. And then u of 2 root 2. Okay, and then we have the square root of u. r dr is 1/2 du. The 1/2 we can move it in front. And then we still have the d theta. Yes. So, what is that? Okay, so this is like u to the 1/2. Integral of u to the 1/2 is u to the 3/2 over 3 times 2. Evaluate. U of 0, 1 plus 0 squared is 1. U of 2 square root 2. So 2 and square root 2 squared is 8. 1 plus 8 is 9. And d theta. Okay. So we have 2 over 3, and then we plug in 9. Square root of 9 is 3. 3 cubed is 27. Minus, when we plug in 1, is 1. D theta. So now you can see we can pull out all the constants. These guys cancel. And 27 minus 1 is 26. Well, but the 26... we integrate the constant, we just get 26 times theta. Theta is from minus pi over 2 to pi over 2. Well, so that is pi over 2 minus negative pi over 2 give us plus pi over 2. So the answer is 26 pi. Okay. And we can also check our answer. This is a half cylinder, right? And you know what the answer is. Right? So cylinder is area of base times height. Okay, so from geometry, we know this volume equals area of base times height. What's area of base? Well, it's half of the circle, right? So pi r squared. Well, r is 2 square root 2. R squared become 8. And what's the height? You see, from minus 1 to 2 minus negative 1 is 3. So, okay, let's see. Okay, so that is, so we have, so this is just 8. 8 over 2 is 4. 4 times 3, 12 pi. So this is the volume. Volume means if we have our integral, and then if this inside function equals 1, we will get the volume equals 12 pi. Okay, we're integrating the same thing, but if the inside function is 1, we'll get the volume. Okay, and now the mass of this solid is like 26 pi. Okay, so this is our density function. Okay, then this guy is like the mass. So far, so good, everybody? Okay, let's continue. Find the volume of the solid D between the cone z equals square root of x squared plus y squared and the inverted paraboloid z equals 12 minus x squared minus y squared. Okay, let's draw the picture. Okay, the cone. This is the cone, right? And we have the inverted paraboloid. So paraboloid, this is 12, and then when it intersects the xy plane, which means z is 0, then we have, if z is 0, then you have 0 equals 12 minus x squared minus y squared. This is the same as x squared plus y squared equals 12. So let's say this is like square root of 12. And then a paraboloid looks like that. Can you see it intersect the cone and we get a circle? So it intersect the cone, we get the circle. And let's project this circle down. So if we project this circle down, we get this circle. And what's the radius of this circle? Let's solve the system. Okay, so here it's better to work with this cylindrical coordinates. So it's better to use r, theta, and z to denote. So let's change in terms of r. Well, this means square root of x squared plus y squared. This is just r. And then the other side, we have 12 minus r squared. See, this is much simpler. And then we have r equals 12 minus r squared. So we move everything on the left. We have r squared, and then plus r minus 12 equals 0. Okay, so let's see. And this is r minus 3 plus 4 equal to 0. This is r minus 4, r equals 3. So actually, the cone does not only include the top cone, it could only include the bottom cone. Okay, so it can also intersect the bottom cone with another circle. So that is when I would say like this number. Okay, but in our case, let's just look at the upper cone. So that is when r equals positive. So far, so good, everybody? Yeah, because our cone is the square root. The square root means is the upper cone. Okay, so z is greater or equal to 0. So that is the upper cone. Okay, and you can see now r is that, so r is positive. R squared equals 0. So we only pick the 3, we don't pick the minus 4. Okay, now you know this is a circle with radius 3. Alright, now we're ready to set up our integral. Okay, so because we want to find the volume, so which is this solid. Okay, everybody? So volume. And we have 1, and then central coordinates r, d, z, d, r, d, z, d, r, d theta. Okay, if we look from the outside to the inside, you see, when we project this solid onto the xy plane, the green disk is our base region. Our base region, the theta goes from 0 to 2 pi, and our r goes from 0 to 3. Is that okay, everybody? The base region is this guy, this disk with radius 3. So just keep in mind the base region, the radius is not square root of 12. So be careful with that. And then z, so you pick any points on this base region and go up, go to the z direction. Then we cross the solids at the surface in these 2 points, right? The bottom one is on the cone. Okay, so z equals r. The top one is on the paraboloid, which is z equals 12 minus r squared. So we 12 minus r squared and r. So far so good, everybody? Okay, let's continue to solve this triple integral. Integral with respect to z, okay, then it's rz. Evaluate from r, 12 minus r squared, dr d theta. Okay, so we plug in 12 minus r squared, minus we plug in r, dr d theta. So far so good, everybody? Let's distribute it. So we have 12r minus r cubed minus r squared, dr d theta. And let's continue. So 0 to 2 pi. Integral of 12r is, so integral of r is r squared over 2, so 6r squared. Integral, so we r to the 4 over 4, r cubed over 3. And then we have d theta. R goes from 0 to 3. So far so good, everybody? Okay, so 3 squared is 9. 3 to the 4th, 81. 3 cubed, there's a 3 under there, so it's like 3 squared, 9. Then d theta. Wow, what is that? Well, that is like 5 copy times 9, 45 minus, 81 over 4, sorry. 81 over 4. And then we can have integral of 1 d theta. It's just theta. Okay? So what is 45 minus 81 over 4? Let me use my calculator. Okay, you can also plug this in your calculator and check your works to see whether we have the same answer. So I got 99 over 4. And then my theta goes from 0 to 2 pi. So it's like 99 over 4 times 2 pi. So you know if you're integrating a constant with respect to theta, you just multiply your answer by theta, right? And our theta is 0 to 2 pi. So multiply our answer by 2 pi. And 2 and this guy cancel. We have 99 pi over 2 is our final answer. So far, so good, everybody? Okay, so that is cylindrical coordinates. And let's take a little break. The next video, we will talk about spherical coordinates. See you soon.